Okay, right. So we're going to compute this Laplacian for that function. Okay. So got to start taking a bunch of partial derivatives. Okay, so here we go. Okay, so u is x squared plus y squared plus z squared to the negative 1/2. Now I'm writing it in that form because that's a little bit more convenient for derivative purposes than that form. Okay, alright, so we're going to start off with trying to compute that term. Of course it comes in two stages. Step one, I've got to take the x partial, and here we go. Okay, so I have negative 1/2 squared plus y squared plus z squared to the negative 3/2, and then don't forget to multiply by the derivative of the inside, which is 2x. So that turns very nicely into negative x times x squared plus blah blah blah. Cool? Okay. Alright, now let's take the x partial of that. Sadly, we have to use the product rule. Right? So, negative 1 times all of this. And then plus, well, now let's see here, negative x. And now I've got to take the partial of this second factor, which is negative 3/2. All that business to the negative 5/2, and then again, chain rule, 2x. Okay. And let's see, we get then, okay, that's interesting how that works out. We have negative 1, oh, that's the same. This 2 cancels with that 2, right? So that cancels with that, so let me lose those, and that minus cancels with that minus, and all I'm left with then is 3x squared. Yeah. Okay, 3x squared. Okay, and okay, good. All right, now I'm going to appeal to your algebraic intuition, and by the way, let me save a little time. Let me just call that uxx. It's a little handy, right? Okay, so uyy, what you want to bet? It turns out to be this. Yeah? Okay. And I'll leave that for you guys to work out on your own. Okay. And likewise, use easy. I won't even write it down. You can guess what that's going to be. Okay. Oh, I forgot my negative 5/2. Sorry, that's important. Yeah? Okay. All right. So the thing that we're interested in is the sum of all three of those things. That's the Laplacian. Right? Let's go back up to the formula up here. The Laplacian is sum of those three second partials. Okay. All right, so I just want to add those three things. It sure doesn't look like it's going to all cancel, but it does. So let me show you how this all canceled. It's a really nice little bit of algebra, and that is let's come up with a common denominator. Our common denominator is that thing. All right, so I'm going to pull out a factor of that. Now, you'll notice that this exponent here is not the same as that exponent. Those exponents differ by 1. So when I pull out that as a common factor, then I'm still left with an x squared plus y squared plus z squared over here. Right? Okay. Okay, so Common denominator, row to the negative 5/2. Okay. So then I'm going to have, I don't know why I didn't think of this earlier, I'm going to use row to represent x squared plus y squared plus z squared. Okay. So I have negative rho squared plus 3x squared, negative rho squared plus 3y squared, negative rho squared plus 3z squared. Yeah? Make sense? Okay. All right. And that I can rewrite as, well, I have negative 3 rho squared from that and that and that, right? But then I also have positive 3 rho squared from that, which gives me 0. It's really hard to see that coming until the very last second there, but it totally works. Yeah. Is that cool?
So how does that show that we have delta u equals 0 everywhere except at the origin?
Oh, well, right, and I was sloppy about that. So this function isn't even defined at the origin, right? So the very first thing that I should have said is that, the following calculation obviously doesn't apply at the origin, at which point there's this massive explosion and nothing makes sense. And so, yeah, right. But everywhere else, this argument's all fine.
Okay.
I mean, as long as this row isn't 0, then we're not taking a reciprocal of 0 anywhere, and so everything's fine.
Okay.
Yeah, right. So, yeah, I should have said that at the beginning. Everybody happy? Okay.